Welcome back to Parallel Programming on the JVM. I'm Daniel, and in this video, we're going to discuss how threads communicate and how you can manage that in Scala. Now, if you're a JVM expert, or if you have lots of programming experience with distributed systems, you may safely skip this lesson, but I'd still recommend you watch it, even as a refresher. So in our IDE in part 3 concurrency, we are going to create a new Scala application just for this lecture. I'm going to call this Thread Communication. Of course, make an object and make it extend app. All right, so we're ready to go. Now, at the end of the last video, we established that with the tools that we know so far, we cannot really enforce a certain order of execution on threads. But with what we learn in this video, in this lesson, we are going to manage that. Now, the sole scenario that we're going to work on is a classical multi-threaded problem, which is called the producer-consumer problem. This problem has many formulations. It's a classical one, but here's the scenario that we're going to work on. So we are going to start with a small container which wraps a single value. And in parallel, we have two threads running. One is called a producer, which has the sole purpose of setting a value here inside the container, and a thread called consumer, whose sole purpose is to extract the value out of the container. Now, the problem is that the producer and consumer are running in parallel at the same time, so they don't know when each other has finished working. So the problem here is that because these threads don't really run in a predictable fashion, we have to somehow force the consumer to wait for the producer to finish its job. Otherwise, there's no real value to process. All right? So the whole problem is all about forcing threads to run actions in a guaranteed certain order, although the threads themselves are not ordered. Now, the reason why this problem is interesting is that in parallel application, we often get into the situations where we need to wait until some data is present, like fetched from the network or computed after some expensive calculation, before we can do the rest of our work. So most of the problems that we are going to encounter in our multi-threaded world are going to be some version of the producer-consumer problem and of other classical synchronization problems. For our goal in this video, we are going to work on versions of the producer-consumer problem because it's a problem that's easy to understand and its impact is immediately visible. So I'm going to start by defining a simple container which holds a simple variable member inside. So private var, let's call this value, which is of type int, super simple, equals 0. So this is the default value. And in the simple container, I'm going to add three very, very simple methods. IsEmpty, which returns a Boolean. And let's just say that the simple container is considered to be empty if the value is at its default. So value equals 0. And we have two methods here to get and to set the value. So def get, which returns the value, and we are going to reset it to 0. So we're going to say val result equals value, then value equals 0, and then return result. All right, so getting the item from the container will reset it to its default value 0. This is the quote-unquote consuming method. And the quote-unquote producing method is going to be set. Let's call this new value of type int, and this will set value to new value. Cool. So how would we solve the producer-consumer problem having an instance of a simple container while two threads are running and one produces a value here and the other must wait until the value is present so that it can take it out? So let's define a small naive producer-consumer, which just returns unit because I just want every piece of logic to happen inside. So I'm going to instantiate a simple container. All right. And I'm going to instantiate two threads. I'm going to start with a consumer. So consumer is going to be a new thread, which does the following. And if we take a few seconds to think about it with the tools that we have no choice but to make consumer wait in a while loop until there is a value inside the container. So just for debugging purposes, I'm going to add some print statements here. So I'm just going to say print line saying consumer waiting. All right. And we have some while loop. And we are going to test whether the container is empty. So as long as the container is empty, I'm just going to wait. So I'm just going to add some print statements. Consumer still waiting. So actively waiting. All right. And at some point, the producer will produce a value inside the container. So this while loop will break at some point, and the consumer will be free to get the value out of the container. So I'm just going to say consumer, I have consumed. And let's just add container.get. So getting the value out of the container will extract the value and reset it to 0. So the logic for the consumer says, as long as the container is empty, I'm going to wait. And when somebody sets the value inside, this while loop will break and I'm free to get it out. Now let's instantiate the producer, which is also a new thread. Now let's say the producer also prints something. Let's say producer, let's call this computing, hard at work. And let's simulate a long calculation by setting a thread sleep. Right, so let's sleep it for half a second. And let's create a value, which is, let's say 42. And I'm going to print that the producer is, I have produced, after long work, the value and the value, which is 42 in our case. And I'm going to finally set, so container.set value. All right. Now let's start our threads. So consumer start and producer start. All right. So let's just call our naive prod cons and see what happens. So if I run this, I see all kinds of stuff. So the consumer is very actively waiting that it prints out, it fills the console with a whole lot of logs. And at the moment the producer produces the value 42, then the consumer breaks the while loop and says, I have consumed 42 and I'm free to finish. So we have, in a way, achieved our goal, because in this particular code, we know for sure that the producer must produce a value before the consumer is able to fetch it, which is our very purpose. Now, the consumer is blocked in a busy loop, so this is busy waiting, until a value is present, at which point it extracts it and then is free to use it as it sees fit. But I think you'll agree with me that this code is pretty dumb because all the busy waiting is computing waste. So let's use some nicer mechanism to write smarter code. But this involves some new tools, and these are called wait and notify. So let's talk a little bit more about synchronized for a second before we move on to wait and notify. So by now you know that evaluating a synchronized expression on an object will lock the object from other threads. So when you say someObject.synchronize, this will lock the object's monitor. Now, what's a monitor? A monitor is a data structure that it's internally used by the JVM to keep track of which object is locked by which thread. Once you have locked the object, any other thread that's trying to evaluate the same expression will block until you're done evaluating. And when you are done, you will release the lock and any other thread is free to evaluate the expression if it reaches that point. Keep in mind that only any refs can have synchronized blocks. The primitive types like int or boolean, they do not have synchronized expressions. Having said that, please keep in mind that only any refs can have synchronized blocks. So primitive types like int or boolean do not have synchronized expressions. Now, some general tips of working with synchronized expressions. Make no assumption about which thread gets the monitor first. As we saw in the previous exercises, there's really no guarantee. Also, please keep locking and synchronizing to a minimum, but still maintain thread safety at all times in multi-threaded applications, because otherwise you'll get into very, very nasty bugs that are incredibly hard to debug. Locking should be kept to a minimum for performance concerns, but thread safety is more important at all times. Alright, so having talked about synchronized, let's move on to our little tools, wait and notify. Cool, so what's waiting? Waiting on an object's monitor will suspend the calling thread indefinitely. So let me give you an example. Say we have some object that's under synchronization. If one of the thread reaches this synchronized expression first, then this will lock the object's monitor and the thread is free to execute some code. But when it calls wait, it will release the lock on the monitor and suspend at this point. And after it's allowed to proceed, it will take the lock on the monitor again and continue evaluating code. Now, from another thread, if we call another synchronized expression, which will lock the object's monitor, then this thread is free to execute some code, and when it calls notify, it will give the signal to one of the sleeping threads that are waiting on this object's monitor that they may continue after they acquire the lock on the monitor again. Now, bear in mind that multiple threads may be waiting on this object's monitor, so calling notify will signal only one of them that they may continue. Which one? You have no control. It's at the discretion of the JVM and of the operating system. But that only happens after they acquire the lock again. But at this point, I'm still holding the lock, so I'm free to execute some code. And at this point, I am done. I will unlock the monitor, and one of those sleeping threads will be free to acquire the lock again. If you want to signal all the running threads that they may continue, use notify all. Now, bear in mind that waiting and notifying are only allowed within synchronized expressions. Otherwise, they will crash your program, so be very careful. Now, what you see on the screen, is the whole JVM Thread Communication model, and we are going to use it to implement a little smarter producer-consumer code. Okay, so we got new weapons. Let's write a smarter producer-consumer. So let's call this smart producer-consumer, and let's write two smarter threads. I'm going to start with a new container, of course. New simple container, and let's call this consumer as before, and we are going to create a thread which does the following. Let's say we'll print line something, say consumer waiting, and within a synchronized expression on the container, we will make the consumer wait. So we're going to say container.synchronized, and we are going to say container.wait. Container. So at the point of waiting, the producer thread will release the lock on the container, and it will suspend until someone else, namely the producer, will signal the container that they may continue. So at this point, the container must have some value, because the only one that can wake me up from waiting will be the producer. So at the end, I'm just going to say consumer, I have consumed, and let's say container.get. Okay, and then we have the producer thread, which is again a new thread, which will do the following. Let's say that the producer will also print line producer, let's say hard at work. All right, so we're simulating a long computation with, let's say, thread sleep, let's say 2 seconds, so we can see the effect. All right, and then we'll produce a value. of course 42 because it's a classic, and in a synchronized expression on the container, container.synchronized, we are going to print something like producer, I'm producing, and then the value. And then I'm going to set the value inside the container. So container.set value. And then I'm going to call the magic method container.notify, which will give the signal to the consumer thread that they may wake up after the producer has exited the synchronized expression. Right? So there's no more code here for the producer, only code for the consumer to execute after they have woken up. So let's start our little threads. So consumer.start and producer.start. And that should be it. Let's comment out the naive prod cons, because this will pollute our console logs. And let's just use the smart prod cons. So let's run this and see what's happening. So right-click run, and let's see this in action. So you see consumer waiting and the producer hard at work, and after it's done, the producer is producing 42, and instantly the consumer wakes up and consumes the value. No more busy waiting. Now, this is the proper way of writing parallel code. Some threads will do a bunch of work and then wait to be woken up by some other threads and then carry on with their work. Now, let's carry this over to the next video because I want us to enhance the problem with many values and with many threads.